here, I'm going to show how we can take a trapezoid. Here's a trapezoid. And this is a special kind of trapezoid. It's motivated by the figure we have here. It's got vertical sides, and the base here is perpendicular to those sides. And of course, then we have a sloping side here. And I'm not using the usual definitions of trapezoid base and altitude. Actually, trapezoid bases are parallel to each other. So if you're talking in correct geometric terms, these would be the bases and this would be an altitude. But if we look at it on a graph, these look like altitudes and this looks like a base. And so I'm going to, usually when I write this out, I call this a graph trapezoid, and it's a very significant construction. So we take the trapezoid, motivated by this picture, trapezoid with two altitudes, actually two bases, but we're going to call them altitudes, and a base, perpendicular to the altitudes. And that trapezoid is going to be converted to an equal area rectangle by simple cut and paste. So we have the midpoint. Remember, we talked about the midpoint velocity here being the average velocity. We take the midpoint of the sloping segment of at the top of the trapezoid, and we draw an altitude there. And we can see that that's an average between the left and the right altitudes. We make a cut across here, so we cut this little triangle off, and we lift that triangle off, and I've marked the triangle, two little tick marks along one of the sides and a single tick mark along the other. I haven't done anything with the hypotenuse. We're going to take this triangle and flip it over and glue it on here. So the hypotenuse will go with this sloping segment here. And the finished figure is going to look like this. And it should be obvious then that what we have now is a rectangle whose area is equal to that of the original trapezoid and whose width is equal to the original width of the trapezoid and whose altitude is equal to the midpoint altitude of the original trapezoid. So the rectangle has dimensions midpoint altitude by the original width. And we'll talk in a minute about what the significance of that is for the idea of velocity and motion. So let's take the trapezoid that's formed by these projection lines and the axis and the sloping segment that represents the way the velocity changes in time. And let's just draw that as a simple trapezoid over here. I've drawn it a little bigger so I can label it. So this trapezoid has the same dimensions as this one. It just looks bigger. V naught is this distance, which is this side. VF is this distance, which is this side. And V bar is the altitude from the base up to the segment at its midpoint, and that's the average velocity. We do the same construction. We cut this little triangle off and invert it, and we end up with a rectangle whose altitude is V bar and whose base is delta t. What's the area of that rectangle? Well, the area is V bar delta t. Now, what's the significance of V bar delta t? Well, recall that V bar equals delta x over delta t, change in position divided by change in clock time. So it doesn't take any great algebraic insight to see that your change in position is going to be V bar times delta t, so that the area of this rectangle represents the change in position that you would have at velocity V bar in time delta t. Furthermore, the area of this rectangle is identical to the area of this trapezoid. so that the area of the trapezoid is also v bar delta t, and the area of the trapezoid represents how far you would go at that average velocity for that time interval. So what have we seen here? We've seen that the slope of the trapezoid is the average acceleration. We've seen that the area of the trapezoid represents the change in position. So in a v versus t trapezoid, slope is the average acceleration. Area is the approximate change in position. Now why do I say approximate change in position? I say that because remember that we just have these 2 points. We don't really know that the velocity is represented by a perfect straight line between these points. If it is, then we have the actual change in position. If the time interval is short enough that the velocity graph is very close to a straight line, then our area will be very close to the change in position.